everyone, today we're going to talk about evaluating limits at infinity, limits with unbounded behavior, and limits of oscillating functions. Get ready to unlock the power of math together. Let's dive right in. So the first special case are limits at infinity. So you can use the limit notation to describe end behavior of a graph. So in previous units and also in Algebra 2, we talked about end behavior with this notation. Now we're going to use our limit notation instead. So the first function we're going to look at are your polynomial functions. Now polynomial functions, you're going to look at two specific things. So the first thing you're going to look at is as x approaches negative infinity. So as x approaches negative infinity, I'm going to be looking at the left-hand side of my graph. So the limit, or what's my graph doing? Where does my graph point towards? I'm pointing up towards positive infinity. So I'm approaching that particular value of infinity. And then you're going to look as x approaches positive infinity. That's the right-hand side of my graph. So what is the value that my graph is approaching? You got an arrow there, so you've got positive infinity. When we look at rational functions, remember that the horizontal or the slant asymptote is going to be the end behavior. So you'll have to look at the end behavior first without a calculator, and then you can confirm if it's necessary. So in letter A, you have a rational function, and we classified this as even Stevens because your degrees were the same. So anytime you had even Stevens, you looked at your horizontal asymptote being the lead coefficients. So 2 over 1, which is the same thing as 2. So your limit at x approaches negative infinity and x approaches positive infinity would be that horizontal asymptote at 2. In the second question, your exponent is larger in the denominator than in the numerator. So we said that that was bottom heavy. So if you had a bottom heavy rational function, your horizontal asymptote would be at 0. So the limit as x approaches negative infinity and x approaches positive infinity would be 0. So in letter C, your degree in the numerator is 2 and it's larger than the denominator. So that was top heavy. So that means you had no horizontal asymptote. However, you do have a slant asymptote. And a slant asymptote was that the degree in the numerator is exactly 1 larger than the degree in the denominator. So we do have to use synthetic division. So we made our 0. So x minus 1, that 0 was 1. We wrote our coefficients. So 2 is the x squared term. There's 0 for the x term, and my constant was negative 5. So we did 2 to drop down, multiply, that gets me 2, add down, multiply, and then add down. This was your remainder, this was your constant, and this was the x to the first term. So our slant asymptote was y equals 2x plus 2. Okay, so that means your graph's going to look something like this, right? So your line. So I'm looking at what our limit is going to be from here. And as x approaches negative infinity, that's the left-hand side. So my graph is approaching negative infinity. And then as x approaches positive infinity, that's the right-hand side. So that value that it approaches is positive infinity. Your next special case is limits with unbounded behavior. So you've seen vertical asymptotes in several different functions. So you've seen them in rational functions, which is this first example here. So let's look and see what we have. The limit as x approaches negative 2 from the left, right? So x approaches negative 2 from the left. What is that value that we are approaching? That is negative infinity. The limit as x approaches negative 2 from the right, approaches negative 2 from the right. So I'm going up, pointing towards positive infinity. So again, left has to equal the right. It does not. So the limit does not exist. Another rational function you've seen, like so, if I sketch a graph, looks something like like this. Here are your branches here. So here we're going to look as x approaches 0 from the left. Here I'm pointing up, approaching positive infinity. X approaches 0 from the right. I'm pointing up, approaching positive infinity. The limit as x approaches 0 from both sides is positive infinity. Here we have a table, so the limit as x approaches 1 from the left. So I'm getting closer and closer to negative 1,000, right? That's here. As x approaches 1 from the right, I'm approaching positive 1,000. And because the left hand does not equal the right hand, the limit as x approaches 1 does not exist. Your next special case are limits with oscillating functions. So again, oscillating just means that it's sort of repetitive back and forth. So you're going to see sort of like these waves. Now, some of these oscillating functions have limits at a point and some do not. So some of them also have limits at their end behavior and some do not. So as you graph this, whether it is in your calculator, whether you do it in Desmos, you want to make sure, especially with these trig functions, you want to make sure you are in radian mode. So here I'm going to just graph cosine of x. Let's give you a sketch here. So I know I got to get to 1 and negative 1. I've got my period of 2 pi. 1, 2, 3, 4. Here's negative 2 pi. And as I draw my cosine, I'm going here, here, down, here, like so, starting from the top. Here, 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 and waving and waving and waving, like so. Okay, so we want to evaluate, let's say f of 0, evaluate just that number. We're going to get 1. The limit as x approaches 0. So I'm going to look from the left-hand side as well as the right-hand side. I'm both approaching the same value, that is 1. And then the limit as x approaches negative infinity. I'm looking at the left-hand side of my graph. That one does not exist, right? You have varying values as you keep going to the left-hand side of your graph, right? You're going to have, let's say at 1, you could have your value be at 0, negative 1, and it will change. It will not be the same. Now, as x approaches positive infinity, look at the right-hand side. And that would also be the same thing because I'm going to wave, right? That graph waves continuously. So that function, as x approaches positive infinity, does not exist. So here we gave you some screenshots in Desmos so you can see how the function will look like here. So let's evaluate it. At f of 0, you have y value of 0. Your limit as x approaches 0, so you got to look at left-hand side and right-hand side. Do they approach the same value? Yes, they do at 0. And then the limit as x approaches negative infinity. Again, that's the left-hand side. You've got varying values, right? So does not exist. As x approaches positive infinity, right-hand side, same thing, does not exist because those values are going to change. So here we got f of 0, again, same thing. As you look there, you're like, oh wait, I can't really see that far in. And you're like, oh, it might be 0. However, this is x, right? So if I plug in 0 for x, you get 1 over 0, which you can't have. You can't divide by 0. It's undefined. Okay. Now you can have a limit as x approaches that value. Do they approach that same value? They get closer to 0, right? So that is okay to have. As x approaches negative infinity, I'm going towards one particular value. I'm approaching negative infinity. And from the right-hand side, we're going up, positive infinity. Thanks for learning with me today, unlocking the power of math one problem at a time. Don't forget to like and subscribe for future notifications on Precalc videos.